Okay, thank you. Thanks for coming. Glad we finally see someone has action. So, every time I come to the news, I come to meetings next door. Not nice. No. Right. Every time I come on, this is Boston syndrome. Because you guys are all theorists. One information. So I really feel bad talking about things without being agreed. In this case, I need to give you an extra help one. Because one is all work in progress. So everything I'm going to tell you has been done by these two undergraduates. Very good undergraduate. The PI really is Gary. My colleague Gary tell you what he will be displayed. So I'm just a spokesperson. But so not only is this all work in progress, we've just got a PhD student to start working on the problem this coming September. But also, I actually currently know very little about the necessary background for either the science or the mathematics. That's why. So this is unashamed attempt to get some of this free consultancy. So I'm hoping that at the end of this, let's take slightly past. We all have to. So, take it all with a pinch of salt, but I think the overall shape of the story is going to be fun. I will be showing you something. Okay, so I'm going to tell you about an organism called Labyrinthula, maybe for short. Why I studied it? Partly because it is, and insofar as I know it is unique, that is either very good or very bad reason for study. It's too unique, no one ever reading the papers or science. That's very bad. But I think in this case, it's actually so uniquely cute that I was initially drawn to it. It turns out it's also extremely important. So I'm now about to give you 5 minutes of the first paragraph of the right application of the So in order to tell you why it's actually important rather than just uniquely cute, let me tell you about seagrass. So under the sea, coastal regions, there are forests of grass. There are basically 4 families of seagrass in the world, not ending with 70 species. And these are cover very large areas on the coast. I'll show you back in a moment. They actually not very primitive because in fact they flower. They're actually land flowering plants returning back to the sea. So they actually do not advanced. They're not primitive at all. Plants grow out in the sea, they're land plants, they have a flower and grow back into the sea. Well, and I mean, I'm pretty much talking very well. Sorry? Is this really important? It's really important. Yeah, fine. So, I mean, you can look at the website, but there are all kinds of reasons why seagrass forests, the coastal region, are ecologically extremely important, especially in the era of climate change. So there's coastal erosion. Seagrass is very important for dissipating energy. Certainly, it traps a lot of carbon particles, so it buries the carbon. Breeds, etc., etc. So seagrass is extremely important for coastal ecology. So the one that I'm talking about is Zostera, because the Zosterae means bird or belt. This is what it looks like. Just to tell you from the biology picture, the physics picture in scale. So this can be 10 centimeters to 10 meters. So the building tall. And this is the worldwide distribution, so they're very important for coastal ecology. I have no idea why it's done in South America. So, as I said, they form forests and they harbor all kinds of organisms, apart from all the geophysical reasons why it's just, and the point is this: if you just look at the coast around Europe, this is a survey done a few years ago. You can see that most species of seagrass, most places actually in decline. The one I'm talking about is Zostera marina. This is Zostera marina, and they are subject to a thing called wasting disease. In fact, this website, which is entirely devoted to Zostera wasting disease, course is about plague of seagrasses. So in the 1930s, for example, there's a plague that wiped out 90% of the northern mountain seas, Zostera population. Well, this is a big number. It rounds up to 100. It comes to you. And the interesting thing is the culprit is this organism I'm talking about, the Labyrinthula, which is the labyrinthine organism that infects Zostera seagrass. It's known as marine slime mold. It's a complete slime mold. I tell you why. It's nothing like it. Slime mold. The interesting thing is, it's like many of these bacteria, even our nasal passages and even viruses, it's commensal to university. It lives on there already. The organism that I actually studied, the actual organism of that is harvested from the river estuary that was in the north of Edinburgh and further forth. It's living there all the time. It just occasionally something in the environment triggers it. It turns pathogen. It just needs to the next to see the trigger is not there on the street. But it's there all the time. Just like the cold virus, most of you once have had one cold sore that lives in us, occasionally stress and then triggered. There's another cold sore. So very little is understood, but people are just now beginning to get back to understand this is extremely important, especially as we global warming and changes in sea temperatures and pH, sea salinity. Who knows what will trigger this happens again? It can be disastrous, especially when there will be all kinds of environmental stresses on it. Okay, so that will become the third paragraph. Reasonably convincing. Who is predisposed to be in my Right. Okay. So in fact, the first report of this thing is from this journal. I'm trying to get my journal on 1867 from this guy who very interesting is from Odessa. So Google translated my journal for the labyrinthine figures, represent creatures of microscopic smallness, from thin level like roundless colorless threads, along which spindle-like shaped bodies, sideways or ones. Actual thing journal. So there's these orange bits on the cells, there are these little threads, and you can begin to see why it may be called labyrinthula, because I'll show you the photo in a moment, it was a labyrinth. So I'm going to play you this loop. So you can see. So, no, right. But basically, it sends out. Oops, sorry. So, I mean, the amazing thing about this meeting, we made it 1970. So when cells form a colony, they then send out these tracks. Send out tracks in front of themselves. These are the cells, often more stimulated. They send out tracks in front of them. And so when you zoom out, it looks like a beautiful labyrinth. So I have a friend who uses these to extract omega-3 oils from statistical purposes. She knew that I was interested in microorganism motility. She said, "You must have looked at this movie." She was right, I was hooked. Just before COVID, so COVID delayed me for 3.5 years. So, he builds these labyrinthine tracks and the cells move along. You can see they can move in both directions. Identification. Trackways and the cells moving along the track. And this is pure. It so happens in this case, pure also is useful, which is nice.
So you told us what makes these tracks. Okay, you saw it. Oh,
We can't so much. Right, so I'll show you that for the moment. I will come back to the later parts of the film. Now we agreed that in 1970s, this is famous. There were no CCD camp, this is a real camp thing. But the first paper that I'll show you summarizes the results of the library. So this is my room. So initially, when you take the thing off the seagrass and put it on agar, these colonies, these are called cysts, and they move like single unicellular microorganisms. It's like the nutrient depletion stage of proper slime. But at some point they stop and send out tracks. So initially, cells form these cysts, and they move like a single organism. And at some point they kind of decide enough of that, they stop, send out tracks, and do the same. I think we'll get better, we can probably get to the bottom of the foot cyst. So far we have of seagrass, always. Anyway, you can see cysts. Let me zoom in on the bottom left-hand corner. We're actually using this table is called an This is a larger scale. It's now we've got established. This is really good to watch the other community. So now you can see why it's called an infant, because it builds itself on networks. Let me show you this bottom left-hand corner. You can see that these processes coming out, and at the moment they make contact these cell students. Definitely bits sticking out. So the three areas of investigation, which I thought would be a great thing to unite the two areas of drug. Anyway, there's microscopy, which is from the active matter people. It's not first mentioned now. What are the nature of the tracks, how the tracks are standard from what's called general extractions. If you've been in the other program, the question is, what is the logic of the network? This is a movement thing. What would we do the network for? What's the logic of the cell movement? How do they make decisions? And how to move, where to lay the tracks? And what's the whole colony computing? Is it doing something? It has evolved to be that way. And then, of course, in the end, how is it related to ecology and pathogenicity? So let me take these three in turn, decreasing amount of detail on one slide. So let's do the active matter physics bit, which is this one. So let me tell you, this is not this, because every time I given this presentation to other people in private, say, "Oh, do you know this paper?" Yes, I know it. So it is not slide mode. This is slide mode proper. This is the famous paper that we took the 20th century, where the Japanese put some slide mode. With some food source, and then the slime will solve the labyrinth that the experimental builds the slime. The reason why it's not this is that this organism, the proper slime one, that the nature of the paper is done, forms what is called either syncytium or plasmodium, words are used in interchangeably. In other words, this whole thing is a single cell. Found by a single cell membrane, one cell membrane. And these little tubes is a part of a cell, and it's got millions of nuclei inside. They're all genetically identical paratogen. So this is a whole lot of cells, cytosis, a lot of cells together. So this is a single cell. There's nothing complicated about it, this is just a fractal single cell. One cell membrane enclosing the whole lot. So each tube is a tubular bit of cell. This isn't. So you must not try to map what I'm going to tell you this. I did, and I got very confused until I sat down beside the actually debate inside. So it isn't. So going marine slime models are maximally confusing. No, this is proper slime. Just showing you obviously doing this in Scotland. So I mean, actually, look at 1931, female permanent lecture, well advanced. So she was notes. The point about those days, you can't take pictures, can you? I always tell students, try drawing what you see in the magazine. So try drawing what you see in the magazine. It forces you to couple it to your brain. What am I seeing? What is the significant things to draw? Because you can't draw anything. So this is what you do. So the guy, they reported this guy who took their 70s. So he did a lot of electron microscopy from micrograph, like is in detail. He came up with this sort of cartoon. I mean, he has hundreds and hundreds of these published, maybe dozens of them. What it looks like is this. This is a cell. Okay? Normal cell, remember. However, this extracellular matrix itself is bound by an outer and an inner membrane. We do complex analysis. This is a problem. Thing completely silent. This thing is not, I mean, the trouble is, the type of thing automatically to bothersome. It is bothersome because it's topological bothersome, but it's bothersome. Bothersome is Greek for pollen. Anyway, so it turns out this thing secretes the membranes. But can you picture? Is there cells which sit inside extracellular matrix that the cell is in fact improvising? The first observation isn't part of it. You get a picture. You've got to get it in the extracellular matrix is bound by an outer membrane and an inner membrane that surrounds each cell.
Just a quick question. So the outer membrane is like a regular lipid type membrane.
No one knows. Okay, but it looks like that in the electron micrograph. So you look at his detailed micrograph and you measure the thickness on it. This is a standard issue lipid membrane. But no one has done the details. Oh, what else can it be? But I mean that's not a proof, but if you measure it and then look at how it stands and the rest of it, it looks like standard issue. So no one has investigated it any further. But it looks like all three are more or less standard issues. The thickness looks right. Okay. So in fact, they even do cell division in science. And topologically, apparently what happens is that the bothrosom seems to secrete the membrane. So it secretes it bubbles out the membrane. When these two meet, they fuse. Close this bubble. When this bubble goes further, when it goes to the outside, it breaks and it forms a new membrane. So he has detailed electron micrograph that shows that this is all certainly what happens. So the bothrosom, this organelle that is unique to the Labyrinthula, seems to be at least in the part of the brain secreting the membrane. No one has told me so far, and I can't figure it out, where the outer membrane comes from. That's a complete mystery to me and to the literature. No one has ever commented, but it's there. So when there was no advance from the 70s to the 2000s, people seem to work on this once every 30 years. Now 23, so it's all. Okay, so this is the state of the art from precedent. So again, lots of them. So this is in fact, they took one of these labyrinths, fixed it in formaldehyde, extracted the marine, decoded what that does, it breaks the cell membranes, it breaks all the membranes. So just the breaks. And then stable rhodamine label for loidin, which is a dye that stains F active, filamentous active. So the lab work is filamentous active. I have a separate slide that will tell you they look for microtubules. There are no microtubules. It's an actin pyrazine. This is F8. The rails are F8. So this is immunofluorescence, the beads that she recognized mice. This is phase contrast, this is beads that she, or things, the big beads, that she recognized mice. So this plus other evidence, if they are presented in detail, with the bits like the general myosin, if you general forces on the rest of it. There doesn't seem to be any myosin 2, there's myosin 1. Maybe just myosin 2 are the ones that we heard hundreds of talks about. A long, chain that wraps around together to form this diamond, long like this. Okay? But this is myosin 1, has a short chain. Myosin 1 is special about it. Instead of the short chain, it specializes in inserting the membranes. So this is myosin 1. The evidence suggests that it's myosin 1, but not myosin 2. That's important. So I mean, these are absolutely fabulous. So this is the cyst. This is the central bit, sending out processes. So first of all, I wanted to see that these rails, they do not go on the substrate. They overhang. So they're overground rails. So if you're thinking of crawling, this is not crawling. Nothing is crawling on the surface. But they are tied to the surface by these little guide ropes. And you can see that these big rails, thinner ones split off from it. So that suggests these are composites. The filaments branch off from the antennas. So you zoom in, this is 5 microns, this is 200 nanometers. So this is a track. And so a track is made of a bundle of filaments. But when the cell goes through, it separates all the filaments. So thus the filament. I'm just putting the rate says. So this is a high magnification electron micrograph, those are optical micrograph, this is electron micrograph, and you can see this is 200 nanometers, there are dozens of filaments, small filaments inside. So what seems to be going on is this. So there seems to be those 200 nanometers stuff inside of these rails. Okay, so the smallest, each one of these is a 5 nanometer actin barbed filament that we know enough. They bundle together to form these so-called microfilaments, and 200 nanometers, typical microfilament thickness. And so a long way to the front of the column, when the things are expanding, they seem to all get together to form these 200 nanometer microfilaments, no cells. But when the cells go inside, and lots of these, they push them microfilaments. Okay, so the speed is something like 50 microns per second, which is okay, but it's at the top end of what we use in pharmacopoeia. The normal cell product. This is at the top end of the speed of pharmacopoeia. And so they put it up inside the glycine, so glycine D is known to give it actin polarization. And so the moment they put it in, the front will always end on tips. But it does not affect, oops. It does not affect the cell motility. In other words, cell motility does not depend on actin polarization. On the other hand, when they add, so the cell themselves are moving about 2 microns per second, so there's an automatically slower thing expanding in the front. So this is definitely the case, but they build the roads first, and then they're going to travel. The road building is a faster speed than the cars moving the roads. And you hope it's that, otherwise you travel jam, right? So the roads go faster. So when they put this truck By the way, this is fast because you've all seen that moving on the corrective side forward on the surface. You don't move on the little side, you get the shape cell and falls on the surface and becomes speed 20 times. But those are microns per tens of microns per minute. This is not a micron per second. So this is fast. This is not crawling. So when they put this drug, I don't even ask me to just problem. Anyway, this drug is known to inhibit the myosin ATPase of it and no longer hydrolyze ATP, so the myosin can't. Okay, so when they put that drug in, this is the number of cells passing a certain point per minute. So it's traffic. The traffic immediately starts. When they wash that drug away, it takes a while, but then it builds. So the cells moving depends on myosin hydrolyzing ATP. So presumably it's myosin working. Actin, the front depends on actin polymerization. That's simple. Okay, so I'm so excited when I read the abstract this paper. This is a new models. It becomes our model means these three pictures. No, this is not even proof by part. This is hypothesizing part. But basically, it is to do with, So this is the. Why is it in? So, right. So this is the matrix. This is where the microfilament bundles are. This is the inside of the cell. This is the space in between. So they're saying there are various ways somehow we're going to connect the myosin to this. And I think it's almost certainly this because when we inhibit the myosin, we draw. But I don't like any of them. So you can draw 3 arms. But somehow the cells, so this is the cell. This is drawing these strands. I don't like any of those because in fact none of them shows the myosin directly inserting in the cell membrane. The myosin one specializes. Anyway, the cells have to somehow have myosin on the outside of the filaments. No one has also designed any detail whatsoever. So there is no one. I don't like the hypothesis. Okay, so that's the sort of microscopic. That's as much as there is in the literature. It depends on what the students do, but it would be quite interesting to hear people talk about, what issues you think on. Really, given this is how much we know, can we begin to propose how likely we want some things that one might measure? So, can I just stop there and see whether there are any issues, questions, right ideas from the microscopics that I'm doing?
So when you showed these isolated cells in the beginning, do they already have 2 additional membranes around the plasma membrane?
I think so. I think what happens is that in fact, anytime you see it, the whole thing is already enveloped in some extracellular matrix, which has both the membranes.
So then is it a way of thinking about it that you have an organelle which is called the nucleus, and you have another organelle which is what you call the cell, and then you have the plasma membrane.
It's something like that. So the question is whether you consider the whole thing a single multicellular organism. That is one of the interesting things about this. And certainly that initial crawling of the cyst, I don't have any other name for it. The whole thing is crawling as one.
I don't know much about myosin 1, but one of the cartoons you showed implied that it was embedded in the inner leaf of the plasma membrane, and if it's just attached to that, it can float around. So it's not going to be
that is indeed an issue. Right. So quite possibly all his models are right, that he has to insert something else that they can, somewhat permanently insert into the ganglion force. Otherwise, you can keep trolling and that big trolling, so nothing happens. Yes. They haven't thought of that. And that is one of the puzzles. So there has been anchored somewhere. And in fact, if you look at, I think that may well be what you say if he's actually the bottoms, then it means that is a fixed pitch. So that may well be.
So the actin polymerization is always in the direction of the polarity and actin. What about the myosin
So-
one? Does it?
They indeed have shown that the rails must have active both polarities, because we see cells turn both ways.
Okay.
But somehow by get to the front, they're all one way. So how it makes the transition from the rails back here, where the cell can go both ways, going to the front, then from the vertical, it goes one way. Oh,
Second question is
so where I am, okay.
so the second question is the myosin always walk in the direction of the polarity of the
Apparent.
but to have
But I don't know how to change direction. You know, at one point, presumably force off one direction and force in the other direction. But they must switch between.
Tracks disappear if they're not used.
We're studying. The informal answer is yes. But we haven't studied it in detail yet. So rows that are not used for long seem to be tracked. But I haven't got a quantitative evidence for it. They've got to look at it. You occasionally see one, but all that's disappeared.
Is it known that myosin is the only myosin there?
Well-
About them going back.
But if we look for myosin 2, recently harnessed into traditional biochemistry, certainly was they do the usual stuff.
That's like 13 myosins, there's some subclasses.
So they also look at genome and all, you know, so even so far as I can judge, they know that's an issue. They try quite hard. And they say there's no evidence of myosin 2, which is a guarded statement. I agree it would be better to have at least someone repeat it. But they did classical biochemistry as well, I guess it's thing. Look at genomes and look at genomes. So it's a careful biology. But I agree, that happened to be absolutely crucial. Before you build a model, you better know which kind of deep outcomes. But you agree, right? It's full of mystery, but it's true, because I don't know anything else that tried to move anything remotely like this, with myosin on the outside of the cell. But unless, of course, I think of the way of thinking of that just one organelle. So, you know, this. Okay.
Yeah, but in vitro, there are lots of motility or writing assays, right, which are to some extent similar.
Maybe sort of setting
So there are in vitro experiments, these writing assays, and they look very much similar, right? We have a carpet of organs,
yes.
and then people have also put
It looks exactly like that. So it turns out that this thing has invented a utility assay. Human years for us. Yeah, that's exactly what it looks like. Except that there I wouldn't do it in a slimy substrate. But yes, but this is exactly what it is. But given that it is in extracellular slime, the force generated is significantly drained on energy from generating the force in the slime. So there must be something in it for it. Right. Okay, so let's now do the macroscopic. I was hoping to hear from people. So what? So I learned this word listening to the other programs, first week's workshop. Did anyone else learn this word? So stigmergy, I didn't know what it meant. So what it meant, the stigma in Greek means mark. So this is doing something according to marks left by other people. So the classic thing is ants. Ant finds some food, goes back and leaves a pheromone trail, and so other ants interact with the first ants via the pheromone trail. And when it becomes unused, pheromone trail disappears and the interaction is. That's what stigmergy. Okay, so the question is this stigmergy or is it very, very much more? I'll leave you deciding. So let's look at this movement. It's not just. So the moment they make contact, these students. But at least in my eyes, there was no evidence as it was doing chemotaxis towards these big start. It was growing uniform, all of them until they on the podium. They can't when suddenly student. So the point is, cells build tracks ahead of themselves. When we told the track building is 10 times the speed of single cell building. So heavily guarded inverted commas. There's forethought. The colonies built in rows before using. The colonies built in rows before using them. Whether I call it colony or single organism, lots of organisms is the second thing. The thing, which is totally into the matrix, is built in rows before it goes into. And then they interact with each other via the rows. So I think that's at least emerging plus plus. That's not the ant building the pheromone and interacting with the ant. It's not that. I think. So this is a mature colony. So I want you to be able to look at all kinds of things now to notice that they move certainly both directions, they can slide past each other. Kinds of things to see. But the row building happens in down here. Some colonies expanding, so I'm zooming in on this mature. The thing look hard enough, somewhere one of the tracks is to be it's a bit of unused track. So what we did, and we took a lot of effort because these cells are blown haywire. So we learn set these movies, magically find the tracks, subtract the cells, and then once you subtract the cell, you have a continuous as a continuous track because there must be a track there. So that took very quick projects to full semesters. Get there. It takes long. So this is not true. Very. So we identify the track network, and then we can now have a student this summer. We now once identified the network, they can now look at the focus on the cells and see how to use the track. That's on. So this is putting the work of both those two students. So I'm identifying the tracks and now see how the cells move about. So this is just we were more or less got it right. We know it's not completely correct. We think we've got enough of it, I just start doing something else. Okay, so it's an undirected network. We can analyze it with weighted and unweighted edges. So so this is a network, this is a node. So we continue to include in networks. In other words, the weight that we put on these is the actual physical distance in microns. What I'm going to show you comes from analyzing 3 lots of 12-hour movies, about 10,000 notes on each movie. There's a fair number of statistics, but we do really fast, actually not. So that's what the degree. So you look at each node, how many tracks are they coming out? So it's mostly free, but it's on dead ends. And the simplest thing you can think of that is mostly free is it depends on the number of level theorems and cell state physics, like the cable free or major nexus. Cable free, so every point is free. Again, I'm not saying I have a cable free, I'm saying that this is not unusual, the things that basically one number. If you ask how many nodes are there, count nodes and count the number of edges, you'll find it in configuration is about 1. It's 1. 4 nodes, 3 edges, you go out, that ratio is near 1. So when I track this, it's a function of time, the network topology doesn't change. And so the thing knows what to do. It's determined to do something that was basically 3 nodes. Oh, sorry, 3 edges for each node.
How do you get 2 degree nodes? And you look at straight up.
Presumably is the problem on it something and there's a little kink on something, and then it comes to a dead end or something. But it's actually not a dead end. But I agree, these are sort of slightly off. But they apparently are there. So this is more than not. He's reasonably sure. We asked. So interestingly, the degree distribution of London streets is exactly mostly through barriers. Now the rest of the paper, in fact, goes to politics and the log scale and the power law back. But never mind. Grossly, London streets are free with few barriers. Interesting. I'm telling you that because eventually I want to ask the question: what is the network built to do?
Have you considered Milton Keynes?
Well, mixed machines is kind of special. It's almost as unique as this, but not nearly as huge. Yes. No, exactly what you said. Okay, so interestingly, I mean, this is where you come back to the microscopics. Anyway, so, you know, they're known to be proteins that are 2, 3, actin related proteins 2 and 3, but nuclease and nucleoside branches. Of course, if this is the major process, what's going on, then of course you will think things frequently. But interestingly, so some of you may know this beautiful experiment. 2003, so the cultures and beads lost was the thing, but knew that nucleus. Filaments, then they put them up to feeding. And interesting, they only get that much live is when they put some catching proud insides that are mostly kept where filaments. Force the most interesting thing happens to the psychologist. In fact, the whole thing doesn't look totally unlike something. So this is interesting. So how about I offer a case of beer and we'll come theory? Not so the distribution of edgelings looks like a not normal distribution. Now, of course, on one level, you can say that what else can it be? Because it has to be 0 and 0 is often different. But interestingly, you know perfectly well that the normal distribution comes from additive random processes, not normal comes from multiplicative random processes, and then they tell us. So interesting, the difference between edgelings. The students have graduated before I spotted that he didn't take more units. No. But the distribution is not normal. So, you know, I would like to puzzle this out. I think that eventually explains the telescopic. So there's a thing called transport efficiency. There are various ways you can define it, but basically, what you're asking is this. Suppose I sum all the Euclidean distances. So the Euclidean distance between I and j is just a straight line between. With the Euclidean distance between these two vertices is 10. The Euclidean distance between V1 and V4 is this length. But the actual length between two nodes is the shortest distance. So the L14 is 22. So you can do it differently. But basically, you ask how much of it is what fraction of it are alternative paths. Those are correct paths. Okay, so for these three sets of data, they're basically 1. So it was almost everything to 1. So if you plot the so-called equivalent Euclidean graph, so in other words, you take the actual graph, you put it on the missing edges. That's called the equivalent Euclidean graph. Can you tell which is which? Well, one of them is the equivalent Euclidean graph, one of them is the marina. I certainly can't remember without actually mining it. But you know, that's what their transport efficiency is telling you. That most points are actually no. It's done by undergraduate project, we haven't checked it yet, but if it turns out to be correct, what that is telling you is that it's going for high transport efficiency. But presumably he didn't do this, so but at the expense of the cost is the total sum of connections. So in other words, if you want to maximize connections, you do this, but there's cost to build and to maintain. And the point is, yes, okay, so what will do that for? Okay, why does it want to build a graph that is very close to the equivalent in the Euclidean graph, where the transport efficiency is high, but the cost is also high? So let me show this to me again now for 78. Now I'm going to show you what happens when you find split. So this is streaming the colony in the middle there, it's streaming mostly radially out. Now we're going to show you, I mean, we haven't done this experiment ourselves yet, but this is yeast, this is food. There's no evidence it's doing chemotaxis towards it until it touches. The moment it touches, watch what happens. Everything streams towards it. Okay, at the beginning, it's, at least on this one movie, there's no evidence that it's making a beeline just for the food. But the moment it touches the food, everybody used their own energy streams. So, as far as I can tell, it's not chemotaxis, but rather, so it is very much different from this. So this is building a road network to connect existing cities. Already know where the important places are. Then you do it one way. But in fact, the problem I want to solve, I think, is that you tell it there's a gold deposit somewhere. You're doing mining, you know where it is, but you're not allowed to do it with your physical map. So you put a random base camp somewhere, and you just build roads. 17 times build roads. You want to cover. So that the moment you make contact with the gold mine, you can only tap gold mine locally, then what you want is maximum efficiency for everybody to use the existing road version. I can use a more analogy in one fine. Again, you just want to cover the place. There are no existing cities. You want to cover the place until the moment you make contact, you want a road network to be as efficient as possible. But you know where you are at the moment, all the resources are going to go along the road. I think that is probably what to do. What evidence is consistent? Okay, so let me stop there.
Like in the previous movie, the roads that were most traveled in here and the ones that were not traveled in ducks once they found.
That may well be, haven't done that. That may very well be. But I don't know whether that affects the speed or not. And again, we haven't done that, but that would be a good thing to correlate. That's entirely true. And there are tracks that do affect the speed.
And in fact, your data, you have the tracks and you also have the original microscope image, so you can get the microscope pixel intensity for each pixel along the track and then just statistics on those. And do that over time, and that gives you a wealth of data and start looking at
So we need to correlate it exactly. But purely on the level of the crudest possible network statistics that you can do, what I'm suggesting that what we want to do is at some point, you want every cell on every row to maximally easy to go somewhere. But that somewhere is random. You don't know where that is yet. So you have a lot of cars and a lot of roads. All you know is at some point in your life, you want all the cars to maximally go somewhere. That appears to be what is optimized. I don't know it's optimized, but that seems reasonable. You know when the sounds at least plausible at this stage. You have a better idea on that. I'm completely happy. There's not even thinking about it.
when I first looking at this, I thought that there'd be a trade-off between the cost of building and the cost of moving. But what you're saying is instead it's the cost of building versus the cost of getting to a random point as fast as possible. And
That's what I'm suggesting.
And the cost of building is really large because these cells have to produce a lot of biomass
Yes,
to make such a density.
That seems crazy.
Yeah. So it better be worth it.
So I think he's doing more, and I think some of these have signaling functions. I think some of them have detecting functions. So how does it know that it is food? So their molecules is often slight tech. So I think there's much more. Anyway, I don't have very many slides. So I'll tell you, we only have one slide of this. I have no idea. But it's already on that seagrass leaf, so it doesn't need any of this mechanism. Actually, so normally it doesn't eat the seagrass, it needs something else. I don't know how. So I'm sure free areas. I think there are more problems that we need. What discussion?
So you highlighted how this is very different from the true slide.
But have you done that sort of experiments like solving maze and finding fossils and they also think migrate they sort of
So
set
that was
up-
like a student, I can say all these things. I've only done 2 undergraduate, two semester time. Yes, that may well be one thing to do. Also, very, I just, I suspect the answer, let me make a prediction. He will build roads along all of. The moment he finds food, he just sent everything down that one road. That is the problem. So it seems that it maximizes building roads everywhere.
So you
And then it suddenly goes down just that much.
so that's quite similar to choose line.
Well, except that, yeah. Yes, the logic is, but the microphysics is not.
Yeah.
Because if that turns out to be true, that's what people call convergent, which turn out was a small number of ways from end theory and so on. Doesn't matter what macroscopic logic is. So no, very good example of convergent evolution. Totally different microphysics. But
When you choose like the maze, you've got 2 fossils, they kill off all the other branches and just treat one branch.
I don't know what in this case they treat them all, but that's my view. So
Thank you so much for the talk. I was wondering, so for a single cell, is the velocity roughly uniform along one track once the track is built, or would it vary like for
again,
shorter
you
or
have
longer
not measured that,
tracks?
but by eye, there's no massive variation. When I look at the movie, nothing draws my eye and say, "Whoa, that one is 6.5." Okay, so at least to the naked eye, and look at the whole movie, nothing jumps out at you and say, "Oh, that one is really fast." But yes, again, now I've got the 4D student can do that precisely that.
I mean, I guess the turns are slower, right? Than the
So when
going
I mean,
straight.
they had better slow down and to slide past each other because in a squeeze each other, they are dynamic track between two of them is very substantial. So the squeezing has to slow down. And sometimes they go through traffic jams. I mean, they all lined up and suddenly one start moving, whole move. So again, I know what those models, or indeed why they wanted to move in both directions. I mean, obviously, once there's food, they're all moving back. But,
Earlier you showed edges versus nodes and showed us a really nice straight line. I'm jealous of that straight line. See, that's
very good street.
But do you expect to? I can get that that's the initial expansion stage when you're starting to form that scaly tree. But then at some point, once it starts to prune edges, I would imagine maybe you're starting to slide back on the same line or something else.
Again, the student gone off, but he didn't tell me exactly at which stage things. There were 1 or 2 little defects. I mean, he forgot to give me the units thing. What stages, but it's not the very initial stage. Because I've already 2 or 3,000, and the lowest point is 2,000 notes. So it's something somewhere.
So you showed the strength distribution between 2 edges. When was this analysis done after the
This is
network?
late. This is done on the biggest thing that he's got.
So if you look at the forming colony, just look at
Right.
from one branch when the next one is forming, would it still be?
Right. So what you're saying is that distribution would be a function of time. I agree. But that one for statistics, so he's doing it in each case with the biggest movement he's got. So I mean, it can't be the same thing.
So is there a maybe is there a threshold, let's say, different nucleation sites becoming where it starts to be these kind of localized? Is it that initially the kind of increases the number of cells there and from there it starts to be clear?
That early stage is health issue. And there are all kinds of little emissions, and so quite often, just because people are electric motion, in really mature colonies, you get little groups of cells that actually do this circular electric motion thing. They do little compartments where all the cells go around and around. And those students just don't get distracted. But yes, but that initial stage, not an issue. As the very old colony, again, they do all kinds of weird things. Yes, we know.
Absolutely not find food. Did they kind of stop, go back, or they just keep on going?
This one, the food is in the aim. So there's no possibility we're not finding food.
Okay.
So starvation conditions we have. No, well, that would be another interesting thing, which is to keep an egg on. There is no nutrient. You do that Jesus right, which is to put a bucket of food and then just move up and keep on what it's doing. The actual starvation conditions. I suspect there's other starvation conditions. It breaks back up into those cysts, which is like the student again on starvation.
Any other questions? Okay, next, listen again.